All right, so let's dive deep into this world of nanocatalysis. I know you're all probably knee-deep in Professor Camargo's lectures over there at the University of Helsinki.
Yeah.
And trust me, I get it. Those notes,
Yeah.
intense.
They are.
So consider this your cheat sheet to understanding the core concepts.
Yeah.
Especially for you master's and PhD students out there tackling this stuff.
Right.
We're talking chemical bonding and catalysis,
Yeah.
the famous Sabatier principle, and how the size and shape of those nanoparticles really shake things up.
It's a lot.
It is a lot.
Yeah.
Ready to dive in.
Absolutely. Let's break down those complex reactions
Okay.
into something a bit more manageable.
So picture this.
Okay.
A tiny molecule strolls up to a metal surface. What happens next? It's got to be more exciting than just bumping into each other.
Way more exciting. It's all about the interaction between the molecule's orbitals and the metal's d-band.
Okay.
Think of it as a delicate dance. Let's take a simple diatomic molecule,
Yeah, okay.
A2, approaching a metal surface.
Gotcha.
Okay.
So A2 is looking for a dance partner on the metal surface.
Exactly. As A2 gets closer, its antibonding orbital, usually empty, dips below the metal's Fermi level. Now, electrons from the metal can flow into this orbital.
Hold on.
Yeah.
Filling an antibonding orbital, doesn't that usually destabilize things?
That's the key. It weakens the bond between the two A atoms
Okay.
in our molecule, making them much easier to break apart on the metal surface.
Right.
That, my friend, is the heart of catalytic activity.
So the metal isn't just a wallflower.
Right.
It's an active participant in this molecular breakup.
Exactly.
But I'm guessing there's a sweet spot for this interaction, right?
Yeah.
Too strong and things get messy.
You're spot on. The bond strength between the molecule and the metal is critical.
Okay.
Too weak, and the molecule just bounces off.
Right.
Too strong, and the products get stuck on the surface. There's a just right zone.
Ah, the Goldilocks principle of catalysis. And I bet the Sabatier principle is our guide to finding that perfect zone.
It is. The Sabatier principle is all about finding the optimal binding energy for maximum catalytic activity.
Okay.
The catalyst needs to bind reactants just strongly enough for the reaction to happen,
Okay.
but not so strongly that the products cling on for dear life.
I'm visualizing a tug of war between the reactants and the catalyst. But how do we actually see this principle in action?
Enter the volcano plot. Think of it as a graph where catalytic activity is plotted against binding energy.
Okay.
The curve often looks like, you guessed it, a volcano.
So the peak of the volcano represents the sweet spot, that optimal binding energy where the catalyst is most active.
Precisely. Let's say we're breaking down formic acid
Okay.
into carbon monoxide and water.
Right.
Different metals will catalyze this with varying effectiveness.
Okay.
A volcano plot would show us which metal hits that sweet spot.
Interesting. A visual tool to identify the best catalyst for the job. Now, how about we take a trip across the periodic table and see how different metals perform in some key reactions?
Let's start with CO oxidation, crucial for cleaning up exhaust fumes.
Okay.
You'll notice palladium and platinum are the stars here.
Why those two?
Yeah.
What makes them so good at tackling CO?
They excel at dissociating oxygen molecules.
Okay.
A must for this reaction, but they don't bind CO2 strongly, preventing it from clogging the surface. It's all about that balance.
What about gold?
Yeah.
It's a precious metal, but does it have any catalytic talent?
Gold, on its own, isn't that great at CO oxidation. It needs a little help from friends, like ceria,
Okay.
a metal oxide. When gold nanoparticles are on ceria, they become much more active.
Interesting.
It's a team effort.
So gold needs a partner to boost its catalytic game.
Yeah.
Fascinating how these metals work together. Now, what about ammonia synthesis? That nitrogen bond is notoriously tough to break.
Absolutely. For ammonia synthesis, iron and ruthenium take the stage.
Okay.
They're reactive enough to split those nitrogen molecules, but also know when to let go of the ammonia product.
Right.
So the reaction can keep going.
Another delicate dance of breaking and forming bonds. But I bet some metals are too reactive for their own good.
Exactly. More reactive metals might break the nitrogen bond, but hold on too tightly to the nitrogen atoms.
Okay.
This blocks ammonia from leaving, essentially shutting down the catalytic party.
A good reminder that even in catalysis, too much enthusiasm can be a bad thing.
Too much of a good thing.
Now, CO hydrogenation seems like a versatile reaction. What are the key players there?
Well, for CO hydrogenation, the CO molecule needs to be dissociated.
Okay.
Metals like iron, cobalt, nickel, and ruthenium are all capable of breaking those CO molecules apart, leading to the formation of hydrocarbons.
So are palladium and copper out of the picture for this reaction?
Interestingly, they're not great at dissociating CO, which makes them less suitable for longer hydrocarbons, but they excel in methanol synthesis. Copper, in particular, is the champion for this process.
So even though they're not the best at breaking up CO, they still play a crucial role in a different but related reaction. Fascinating.
It all goes back to those specific binding energies.
Right.
Copper's unique electronic structure allows it to facilitate methanol formation without getting bogged down by CO dissociation.
It's amazing how subtle differences in electronic structure can have such a huge impact on what these metals can do.
Yeah.
Now, for our last stop on this periodic table tour, let's look at automotive exhaust catalysis.
Yeah.
That's a critical process for reducing harmful emissions.
Indeed. We need a catalyst that can convert carbon monoxide and nitric oxide into less harmful carbon dioxide and nitrogen gas.
Right.
The tricky part is that nitric oxide needs to dissociate while carbon monoxide needs to stay intact.
Sounds like a delicate balancing act.
Yeah.
Not all metals can handle that kind of pressure. So who are our environmental heroes in this scenario?
Rhodium and palladium are the winners here. They dissociate nitric oxide efficiently while allowing carbon monoxide to react with oxygen on the surface to form carbon dioxide.
A dynamic duo cleaning up those nasty pollutants. These examples really highlight how the choice of metal can drastically change the outcome of a reaction.
For sure.
But hold on.
Yeah.
There's another layer to this catalytic puzzle, right?
Mm-hmm.
The size and shape of the catalyst,
Absolutely.
especially at the nanoscale,
Yeah.
can also play a huge role.
You're right. That's where we enter the world of structure sensitivity, where the size and shape of nanoparticle catalysts can dramatically influence their performance.
Okay.
But before we dive into that,
Yeah.
let's take a moment to digest what we've learned so far.
Okay.
Anything in particular that stood out to you?
Yeah. It's amazing how, even tiny tweaks
Right.
to a catalyst's composition can lead to such significant changes in its performance.
Yeah.
It really highlights the complexity of the chemistry happening at those surfaces. It's like those metals have distinct personalities and preferences when it comes to reactions. But you mentioned structure sensitivity earlier. What exactly does that mean in the context of nanocatalysts?
Structure sensitivity basically means that the activity of a catalyst can change depending on the size and shape of the nanoparticles.
Okay.
It's like how a building's function depends on its architecture.
Okay, so not all nanoparticles are created equal.
Exactly.
Their shape and size actually matter.
Think of it like this. In structure-sensitive reactions, the rate at which a catalyst converts reactants to products is influenced by the arrangement of atoms on the nanoparticle surface. Change the size or shape, and you change those arrangements.
So it's like building with Legos.
Precisely.
Different arrangements create different structures with different functions.
And the sensitivity arises because different sizes and shapes expose different surface facets.
Okay.
These facets, like different sides of a building, have unique arrangements of atoms, which in turn affect how they interact with molecules.
I'm starting to see how this gets complicated. So if you want to optimize a catalyst, you need to consider not just the metal, but also how you sculpt it at the nanoscale.
That's right. And this is where things get really interesting. We can delve deeper into why structure sensitivity matters.
Okay.
It all boils down to the coordination numbers of those surface atoms and how it influences their electronic properties.
Coordination numbers. Refresh my memory on that one.
It's simply the number of nearest neighbors an atom has. Think of it as an atom's social circle. In catalysis, an atom's social life is key to its reactivity.
So the more neighbors, the more influence from the surrounding atoms, which ultimately can affect the catalytic activity.
Exactly. One way to think about this is through D-band width.
Okay.
This is a region of electronic states in transition metals crucial for bonding. The width of this band changes based on an atom's coordination number.
Okay. I'm following so far.
Yeah.
So how does this D-band width tie into the activity of a catalyst?
As the coordination number decreases, meaning fewer neighbors, the D-band width also decreases.
Okay.
This results in more localized d electrons, making them more readily available for bonding with those molecules that stick to the catalyst's surface.
So it's like those atoms with fewer neighbors have a stronger grip on their electrons, making them more eager to interact with other molecules.
That's a great way to put it. This stronger bonding can significantly influence the catalyst's activity.
This is getting pretty complex. Is it all about the geometric arrangement of atoms, or are there other factors at play,
Excellent question.
like electronic effects?
It's often a delicate interplay of both.
Okay.
Let me give you some specific examples to illustrate.
I love examples. They really help bring these concepts to life.
Let's start with reactions that involve breaking single bonds, like the CH bond in alkanes. These typically happen over a single metal atom on the surface. And what's fascinating is that the activation energy, the energy needed to kickstart the reaction, is lower when the metal atom has a lower coordination number.
So a metal atom with fewer neighbors is actually more effective at breaking those CH bonds.
Precisely. And this is often seen with smaller particles. As the particle size decreases, you get more of those corner and edge atoms,
Right.
with fewer neighbors compared to atoms on flat surfaces.
So smaller particles mean more reactive sites. That's a neat trick.
Exactly. A good example is steam methane reforming,
Okay.
a process that produces hydrogen gas from methane.
Right.
This reaction relies on CH bond activation, and its rate increases as the particle size of catalysts like platinum, rhodium, iridium, and palladium decreases.
Smaller particles equal faster reactions. It's like a
Yeah.
catalytic efficiency boost. But what about reactions that involve more complex molecules, not just breaking single bonds?
That's where the arrangement of atoms becomes even more important. For reactions involving molecular pi bonds, like those in carbon monoxide, nitrogen, or nitric oxide, you need an ensemble of atoms, often arranged in a step-like formation on the catalyst surface.
So it's no longer a solo act. It's teamwork at the atomic level.
Right. Take CO dissociation on ruthenium.
Oh.
The energy barrier for this reaction is significantly lower on a stepped ruthenium surface
Okay.
compared to a flat one.
Why is that? What makes those steps so special?
The steps allow the CO molecule to interact with the surface in a more favorable way. On a flat surface, both the carbon and oxygen atoms in CO have to bind to the same metal atom. But on a stepped surface, they have more freedom, which lowers the energy needed for the reaction to happen.
It's like those steps provide more wiggle room for the molecules to interact with the surface, making the whole process more efficient.
That's a great way to think about it. Another advantage of those steps is that the CO molecule doesn't have to bend as much to interact with the surface, further lowering the energy barrier for dissociation.
So those tiny steps on the surface have a huge impact on the reaction.
Yeah.
It's incredible how these subtle features at the nanoscale can make such a big difference.
And that's just one example. There's a whole world of complexity.
Yeah.
When it comes to structure sensitivity in nanocatalysis, we're essentially architects designing and building structures at the atomic level to drive chemical reactions with incredible precision.
It's mind-boggling to think we can manipulate matter at such a tiny scale. So we've gone from chemical bonding basics to the Sabatier principle and explored how different metals perform in various reactions. We even zoomed into the nanoscale to understand how structure matters. It's like we've unlocked a treasure trove of catalytic knowledge.
And we're not done yet. There's another fascinating aspect we need to explore: cooperative behavior between nanoparticles. Imagine nanoparticles working together to enhance their catalytic abilities.
It's like a team of tiny robots working together to accomplish a big task. This is getting more and more intriguing. So what can we expect from this cooperative behavior in the world of nanocatalysis? Okay, so we've talked about individual nanoparticles and how their structure affects their catalytic activity. Now let's dive into this idea of cooperative behavior. How can these nanoparticles actually work together to boost their performance? Is it like some sort of nanoscale team spirit?
It's more like strategic partnerships.
Okay.
When nanoparticles interact, they can create synergistic effects
Right.
that amplify their overall catalytic power.
So it's not just about the individual players, it's also about the team dynamics. How does this partnership actually work at the molecular level?
One way is through the creation of active sites at the interface between nanoparticles.
Okay.
These interfaces can have unique electronic and geometric properties that enhance catalytic activity.
So it's like creating a catalytic hotspot where different nanoparticles meet.
Exactly. Think of two different types of nanoparticles,
Okay.
A and B, coming into contact. The interface between them can create a unique environment, maybe favoring the absorption of specific reactants or stabilizing important intermediates in the reaction pathway.
So they're essentially working together, passing the reactants along like a well-coordinated assembly line to optimize the reaction.
That's a great analogy. And this cooperation can lead to some remarkable outcomes. For example, bimetallic nanoparticles, those made of two different metals, often exhibit significantly higher activity and selectivity compared to their monometallic counterparts.
Bimetallic nanoparticles, the best of both worlds. It's like combining the strengths of two different players into one super catalyst.
Precisely. And the possibilities for tailoring these bimetallic systems are vast.
Yeah.
By choosing the right metals and controlling their arrangement within the nanoparticle, we can fine-tune their properties for specific reactions.
So it's like having a whole toolkit of catalytic building blocks to play with. But how do we actually control these interactions between nanoparticles? Is it like trying to herd cats at the nanoscale?
It's definitely a challenge.
Yeah.
But researchers have developed some clever techniques. One approach is self-assembly, where nanoparticles spontaneously organize themselves into specific structures based on their inherent properties.
So it's like giving the nanoparticles a set of instructions and letting them figure out the best arrangement on their own.
Exactly. Another approach is templating, where we use a pre-designed scaffold to guide the assembly of nanoparticles into desired configurations.
It's like using a blueprint to build a specific catalytic architecture.
Precisely. These advances in nanofabrication are opening up exciting possibilities for designing next-generation catalysts with incredible precision and control.
This whole field of nanocatalysis is mind-blowing. We've gone from basic chemical bonding to understanding how structure and even cooperative behavior influence catalytic activity. It's like we've uncovered a whole new world of chemistry.
And this is just the beginning. There's so much more to explore and discover in this field.
To all our listeners, especially you aspiring chemists and material scientists tackling these concepts in Professor Camargo's class, remember that this is just the tip of the iceberg. Keep asking questions, keep experimenting, and who knows, maybe you'll be the one to make the next big breakthrough in nanocatalysis.
The world of chemistry is full of surprises, especially at the nanoscale, so keep exploring and stay curious.